Thanks, Jessica. Thanks for inviting me. And wow, I get to go last. I never get to go last. And so that means I get to give the final wrap-up. And as you see, this is a summary of advice. And to some extent, it's a summary of my advice to you guys. And to some extent, it's a summary of what I've heard from the other speakers today. And so let's go through a little bit of it. And so from the technology world, you know, you have Joel and Paul weighing in, and my old boss, Dan Golden from NASA, was one of the original Agile guys, said faster, better, cheaper, and of course, when he made a mistake, it cost $500 million a piece. So could be worse. And then, you know, go to the popular culture. You get a little bit of repetition of the same types of ideas from high and low culture. And you get Danny DeVito weighing in on the idea of leverage, that it's important to move fast and so on, but you might as well do it with somebody else's money if you're going to fail. Okay, so my conclusion from all that is here's the recipe. You start small, and all you guys are doing that, and Y Combinator is an innovator in that idea of trying to see how far you can go from starting small. Leverage what you have, go fast, and I think the most important part here is building in this positive feedback, because if you're going fast in the wrong direction, it doesn't matter how fast you're going. And my favorite, you know, I've heard lots today about all these business books that you should read and buy and enjoy it. And I don't know, I don't have that much patience for these business books. I always buy them and say, wow, that would have been really great if it was a 5-page blog post. But because of the way the publishing industry works, you know, it had to be a 300-page book instead, and I had to read the same thing over and over again. But the one memorable sort of business piece of advice I remember was from John Cleese from Monty Python. And he had a little bit which was he presented as a children's book, which was the children's book of Gordon the Guided Missile. And the idea that Gordon set out on his path and he would go in the wrong direction, but then he had this inertial guidance system and he would adjust a little bit and he would go in the right direction, and then he'd get off a little bit and adjust a little bit more, and in the end it was a happy ending when he blew up at his correct target. So thanks to John Cleese for that, and that's what all you startups have to do. You have to build in these processes to say, sure, you got to go fast, but if you're not getting feedback to figure out if you're going in the right direction, it doesn't matter how fast you go, and then you iterate. So that's the conclusion, and we can all walk off stage now and go home. But I'll say a little bit more, which is I want to give you one other sneaky way to do that, to build in the positive feedback. And that's to do that through acquiring lots of data and running machine learning over it and running these algorithms. And the key here is that no matter how agile you are as coders, and I understand that you're all great, data is going to be more agile than code. Because you've got to write the code yourself, but the data you can leverage. As Danny DeVito said, it's other people's data. They generate it for you, and you just get to use it. And so there's an immense multiplying factor that way. And of course, there are these nice known learning algorithms to give you that positive feedback. So let me just show you some examples of it that we've been able to do at Google. So here's one example. The idea was to improve image search using additional types of data. Now, the secret, or I guess it's an open secret, is that Google and most of the other image search properties tend to throw away the images. And instead, we just look at the words that are nearby. So when you search for Mona Lisa, what you're really saying is, give me an image that has the words Mona Lisa somewhere nearby, and then do all that fancy Google PageRank foo and all that other stuff and show me a bunch of the results. And this is what you get. And sure, some of them are really good results, but some of them are not so good. And the question is, how can we add other data into that? Well, you know, one obvious thing you might say is, well, how about click-through data? That's got to help, right? Because users just tell us what to look at, and we got lots of users. That's got to be a great source. And in web search, that's actually a pretty good source. In image search, it's not so good, and it's because of this attractive nuisance problem, that people are searching for the Mona Lisa image, the one that we actually got there at the #1 result. But when they see that cartoon, they're going to click on the cartoon. And then we're going to boost that up. And I think I did this search with Safe Search on. And if I did it with Safe Search off, boy, there'd be some images up there that would get very high click-through rate. And so you can't, there's some data that you can trust to some degree, and other data you really got to be careful about. But there's other data. You can actually do computer vision techniques, and you can do these very low-level features, and the thing that's all the rage these days is these things called SIF features, these scale invariant features. And so you just take every image, you extract these low-level features from it, and then you do a search, you get back 1,000 results, you take 1,000 times 1,000, compare them all, and see how far apart each one is to each other. Then you make a graph of those comparisons, and you get something like this, and you get a bunch of the outliers on the outside, which are the cartoons and the naked Mona Lisas and so on, and then the inside, you get the canonical ones. And it's just a graph, and we know how to do all these graph algorithms, so now we're done. We got this additional source of image that was there, the source of data that was there all along, but we weren't paying attention to it. And when we do this, we cut down the number of bad images by a factor of about 5 or so. So that's using data that was there to do better. Here's another example for Lincoln Monument. And here, there's actually 3 clusters. Maybe it's hard to see, but in the upper left, there's a sort of the inside at day. In the middle, it's the inside at night. And at the bottom there, it's an outside view of the monument. And they all cluster together. And so I think this is another important property, is that when you start using this data, there's lots of machine learning algorithms you can do. And if you have an algorithm that insists on a one-to-one correspondence between the labels that you're looking for and the exemplars of them, that's probably not going to be good enough. Because if you have a lot of data, you're going to have multiple possibilities. So you want something that can deal with that, that can say there's not just one meaning for this query, Lincoln Monument, there's 2 or 3 or more. Okay, so we did that and it works. Now let's move on to the problem of text. I want to start off with a simple problem in text, the problem of segmentation. So in Chinese and many other languages, there are no spaces between words, so in order to be able to read that, you got to just know where the words are. Now, as a non-Chinese speaker, I can't really do that segmentation, but I can pretend that we had the problem in English by taking English text and eliminating all the spaces. And so if I get a text like this, now I have the same problem the Chinese speaker faces, and I look at that, and as a speaker of English, it's pretty easy for me to segment that and come up with the right answer. Now, is it easy for a computer to do that? And if so, how much do you have to know? So I can do this because I know well-known expressions, I know common words and so on, and I know the grammar of English, and I know the meanings of all these words. How much of that do I really need? Well, let's see. So we can define the segmentation problem as saying we have a text, a sequence of characters, and to segment it into, to take the sequence of n words and segment it, we take the maximum over all possible points I in the text where we could split it into 2, and then take the probability of the first one as a single word times the probability of the rest of it as a sequence. Got that? Good. So essentially what we're saying is take the maximum of, suppose I thought the first word was just the n and the rest is hours the time and so on. Or maybe the first word was just no, or maybe the first word was now and so on, and just take the maximum of that and then we're done. And so that's a little recursive routine. You can code that up in about 3 lines of program and then make it a little bit more efficient. But of course, there's a recursive part, and then there's a base case where we need to know the probability of a single word. But that we can just estimate from a corpus. We can just go out, collect a lot of words, and say how common are individual words. Now, I happen to have 1.7 billion words on my laptop, so I could do it over that. If I was doing this at work, I'd probably go for 1 trillion words rather than a lousy billion or so. But the point is that everybody can do that, right? Everybody can get 1 billion words. It's not that hard. And so go out and get them and see what you can do with them. So I did this. I wrote this little 6-line program or whatever it was, gave it some test data, and achieved 98% segmentation accuracy. And I'm sure if I played with it more, I could make it better. The types of errors it comes up with. So here's one. See if all you guys can run your segmenter in your head and come up with the answer for that. I got base rate sought to, and it should have been base rates ought to. You know, so I was wrong, but that seems like a tough one. Here, this one, My algorithm got small and insignificant where it should have been insignificant. So here's an example where it seemed like I'm missing. So 98% of the time, just knowing the frequency of words seems to be enough. I don't need to know anything about the semantics of English. Here it seems like I have to know a little bit about the semantics, about the relationship between small and significant, and I could get that either by having some model of the meaning of those words or by just looking at a larger window to say, rather than just look at one word at a time, let's look at the probability of pairs and triples and quadruples of words. And then this one's a little bit harder. Can you segment that? My system came up with G in or mouse go, but it should have been ginormous ego. And the problem was that in the 1.7 billion words of training data, it hadn't seen the word ginormous, and I had to estimate that probability, and I made that estimation wrong. And that's always the hard part, is extrapolating rather than interpolating. So that's a lesson to remember. Okay. And you say this can be a trivial problem. Who cares about segmentation? But mistakes were made. People have registered domain names whose segmentation were ambiguous, which they have grown to regret. For example, who represents? Oh, what happened? Okay, I'll just read them to you then. Is there anything I can do here? No? Okay. This is not nearly as funny if I have to read it to you, but there's a site called Who Represents, which talks about which agents represent who. This guy wins the prize. There's another site which helps you find the correct therapist called Therapist Finder. You guys are sharp. Yeah, Paul and Jessica, you're investing in the right guys. There's one that I've actually used called Experts Exchange, where if you move the S over one, you get what you don't want. There's a purveyor of pens and other fine writing implements called Pen Island. And so on. Okay, so you got to get this stuff right. Now, but still, you know, this is all at the kind of lexical level, and I could show you spelling correction, and that's still at kind of the word level. Can you go beyond that to kind of the semantic level? And here's where I really wish that we had this projector back again. Anybody? What's going on? You're the projection guy. Okay. Okay. So one of the first applications we did when I got to Google in 2001 was actually done by Simon Tong, who's a graduate of this university at Stanford, we call Google Sets, where the idea was you put in, it's coming back. You put in Pablo Picasso and Henri Matisse, and we come back with this list, and the more central members of the set are at the top, and the more peripheral ones are at the bottom. And you see, it's all pretty good. Most of them are painters. Paul liked that. A lot of them are these impressionists and from a similar time period. And then you got a few outliers. There's the Andy Warhols and the Norman Rockwells and the Ansel Adams. They aren't quite in the same category, but pretty close. If you give it lions and tigers and bears, you get back a bunch of animals. But here there's some mistakes that look much worse. So how did cotton and musical get in there? That seems weird. And those were all circus animals are very closely related. What if we gave them two mammals that are more distantly related? What do you think it would come up with from that? Any guesses? Yeah, you got it. And there again, it's giving you a good indication of the canonical commands, the cat and man and ls and cp, they're right up at the top, but the weird ones like make node are off in the periphery again. So it seems to have a pretty good feeling for clustering these concepts. Now, how would you build something like this? Okay, so again, you look for data. Now you could spend all day trying to write down rules for how to cluster these, but it's better to not to spend your time doing that. You don't want to be the coding. It's more agile to work with data. So you look at what sources you could use. So one is you just go to the web. You say, lions and tigers and bears, are there any passages on the web where those co-occur? And you go and you look in IMDb, and sure enough, there's one. And you say, well, maybe that's evidence that they go together, and maybe some of those other words do, but it's not that much evidence because some and but and are also in there, and that shouldn't count. So let's look for, are there places where we can get more structured data that's better guidance than this? So you can look for things like semi-structured HTML markup, where we have elements of lists that maybe are hyperlinked or bolded or otherwise broken out into smaller chunks. And now we can say these appear in a parallel structure in the DOM tree. Maybe they're related to each other. That seems like much stronger evidence. You can go to your logs and say, here's one of my users. He was searching for cheetah pics first and then for jaguar. Maybe that means they're related. And again, these are all noisy clues. You don't trust any one of them, but if you have enough data, they add up and do the right thing. Here's another example that shows you where some of that variance sneaked in. So we probably thought of those as being animals, and they are, but the web, of course, is mostly about commerce. And so not only there are the animals, but there are also the things to buy. And a lot of people want to sell children's toys, and so you get categories like bears, but you also get categories like wooden and cotton and so on. And so that kind of stuff sneaks in. And if you're more clever, you could figure out ways to separate out those two separate models. And then another way to do it, and Professor Marty Hurst at Berkeley was an advocate of this, was to use simple natural language processing. And she proposed looking for key phrases where you could just kind of grep for those pages rather than having to parse the whole sentence. And one such phrase is a phrase such as. So if you're looking for other things that would cluster with lions, search for the phrase such as lions, and then look at the things that are comma delimited after that, and those are pretty good representatives. Now, of course, there's a million ways in which you can say that lions, tigers, servals are related to each other, and this will only find the way that happens to use the word such as, so it'll be very poor recall in terms of the percentage of sentences that talk about those facts, but it'll be very high precision in terms of if you get one of these, you really know how to understand it and parse it, and it's going to be good, reliable data. And when you have enough data, you can afford to make that kind of trade-off. Okay. So that was the point I wanted to get across, that you got to be agile, you got to keep improving continuously, and if you work with data rather than code, that's one way to leverage it and get a step up and make that whole process faster. And Jessica can decide how much time we have left.
We have 5.5 minutes.
Okay.
Is it working?
Yeah.
Ever since I read the book that you were one of the authors, it was called Artificial Intelligence, The Modern Approach. I always wanted to ask you, so when do you think we'll succeed, and where do you think success will come from? By success, I mean fully functional, general purpose artificial intelligence. Will it come from academia, or will it come from established think tanks like Google, or will it come from some unknown little startup out of Minnesota?
Well, I think we already are succeeding, right? Because we're able to do things every day and solve problems and recognize images and translate languages and drive cars through the desert without crashing into each other. So that all seems like success to me. Now, if you only define success as can we duplicate a human, well, maybe that's a harder goal. On the other hand, I've done that too. I got 2 kids, and you know, they're pretty smart. So, I don't know if that's the goal we need. We don't need to exactly duplicate humans. We need to augment or work with them in different ways. And sure, we'd like to be smarter, and I think we will see that. I think we'll see much more advances in robots and in online interactions and so on. And we're already getting to the point where most of your calls to service are answered automatically at first. So I think it'll seep in, and I don't think it'll feel like, there is talks of these discontinuities or singularities where all of a sudden everything takes off. I think it'll be more gradual, where you'll just gradually get to take for granted things of robots and so on doing more and more. And I think it'll come from, so if it's gradual, it means it won't be just from one place in Minnesota or anywhere else. It'll just be an accumulation of incremental improvements. So that's just my guess.
Thank you.
Yes, good afternoon. I'm consider myself a semantic web evangelist, and that's, for me, it's the future of the web, and the whole W3C is working on it. So several questions. What's your opinion on it, on semantic web? What is Google doing? Yahoo just said a couple months ago that they're going to do semantic web for their search. Because the questions that you were posting right here about all these data sources, if you have ontologies that represent knowledge, you can actually get all this information and you have all the data that's linked, then it would be much easier. So what's your opinion on it, and is Google doing anything about for semantic web?
Yeah, so semantic web, the future of the web, and always will be. So I think there's already lots of semantics on the web, and I showed some ways in which you can pull it out. And now the question is, how small of a box do you want to push that semantics down into? And I think it's great if a community can get together and agree on that. And I see some places where that's happening. In the biogenomics area, there seems to be pretty good progress where people are building ontologies and sharing them and using them. And I think that's a good model. And it's a good one because it's a community that has a need for that, because they started off with different ontologies. The mouse guys had a name for a gene, and the E. coli guys had a name for a gene, and then all of a sudden somebody discovered, hey, that's the same gene. We've been calling them different things, and so they needed to have a vocabulary that crossed between them. It's also a good community in that they're academic and, for the most part, friendly rather than competitive, and so nobody's trying to spam each other or shoot each other down. And so when you have those kinds of attributes, I think that will coalesce together and it will grow. But I think for the world as a whole, you won't necessarily see that.
But don't you think like the linked data project is something that can show off and can show people, look, you can get linked data all around and
Yeah, so I think we need more flexible ways of linking data. I think the semantic web is a treaty that's made between parties to say we're going to agree on this particular ontology. And the more treaties, the better. But you shouldn't expect everybody to lay down their arms.
But Google
and
isn't
read
interested,
everything.
even though Yahoo is.
No, sure, we're interested. And somebody asked me this a while ago, and I did the computation, and I said, well, if I assigned engineers to formats based on the percentage of pages that had those formats, then the correct number of engineers for the semantic web was 0. Now that's probably not the right way to assign engineers, and so we do want to support it and see where it goes. But so far, we don't see it making an impact yet.
All right, thank you.
Hi, Peter. I guess that a lot of the work you do at Google is taking work that originally happened in a more academic or theoretical setting, and then figuring out how to apply it to actually, make products that people use better. I'm wondering if you have any advice or recommendations on how entrepreneurs can take computer science research and actually apply it in practice, and how researchers can make sure the work that they're doing is actually relevant to real-world problems and actually can be applied.
Yeah. I think what you want to do is start with your problem, not with the research, right? So say, what's your problem, what are you trying to solve? And then when you hit a wall, now go look up and see if other people have tried to solve it in some way, and then figure out how to apply that to your situation. But I think, most of the time, everybody's situation is unique, and no matter what's gone before, it's good to know about it. You don't want to be ignorant of that, but you're not going to be able to just take things off the shelf and plug them in. You're going to have to figure out how they work, scale them up to the scale that you're dealing with, apply them to the particulars that you're dealing with, and so on. And so it's not like just using it, it's like understanding it and then solving a new problem.
Okay. Maybe just a quick follow-up. I'm just wondering, so in terms of people doing the research, how you can make sure that the research you're doing actually does end up being something that is attacking real problems and that is relevant to the problems that are maybe easier to directly observe when you're in an environment like Google.
Oh, wow. I don't know. Try to find interesting problems. Try to find things that people care about, and then publish them, talk about them. Ask Michael, I guess, about how to get publicity for your work.